Okay, so some hints for the exercise 3. Let me go and open my Octaves next. All right, Octave users, you may want to load your signal and control packages. On Matlab, you don't need to do this. So basically, if you are using Octave, you should do package load control and package load signal. That's somewhere on these exercise instructions somewhere. I couldn't find it myself last time. Okay, but anyways, so let's think of a system. I will start it from different point of view. You will have actually this flow chart to work with, but basically where I'm starting it is from zero pole plots. Just to show how to generate these system coefficients from zeros and poles instead of from a picture. Just to show another view. Okay, zero pole plot. Let me mark a couple of zeros here, where this angle is omega 0 equals 3/4 of pi. And then I will mark a couple of poles on simple places. So we have 0.5 times j minus 0.5 times j, and here we have 0.5. So simple coordinates. It should actually give me these poles are inside of unit circle because the radius is 1/2, right, 0.707, something like that. So a stable system. And based on the theory what I showed you earlier, I should get the amplitude response should look more or less like, well, here we have Fs/2. We have the amplitude response going 0 here, and we have local maximum here. Maybe it looks like something like that. I don't know. We will take a look. We will see it in few minutes. Okay, so if we have a system defined, by the way, how about the font? Is it big enough for the back row? I can also rent binoculars. But okay, so this system defined by zeros and poles. So this is an example. Example only. Zeros, these are on polar coordinates. Z equals exp of minus j, not minus j, sorry, j or I, either or, times 3 over 4 times pi. Times pi. That's the complex angle there. And we also need the complex conjugate of that one. I will show you how to do it. So we need a complex conjugate just because I said so. Otherwise, you wouldn't get any real numbers for the system coefficients. So the system coefficients, in order to do any sensible calculus, you need these to be real numbers. So I can actually add there the complex conjugate pair. Oops. Simply by saying, okay, we have a vector, column-wise vector, so it's 2 times 1 vector, and it has this first point, and then semicolon, actually the same as new line on when you are creating tables, and then we have the complex conjugate of that one. So there we have a complex conjugate pair, 2 coordinates. how MATLAB Octave actually separates between the system coefficients and zeros and poles. If you noticed when you asked this, calculate the roots of the polynomial on the previous exercise, you got a column-wise vector. So that's how. So if it's a single row vector, then it's a system coefficient. If it's a single column vector, then it's a zero and pole, zeros or poles. Okay, so that's the zeros. Next, the poles. This is easy. Pole equals to 0.5 plus 0.5 times j, semicolon, oops, plus, it's easy if you can type, 0.5 plus 0.5 times j, and then another row is 0.5 minus 0.5 times j. So again, we have complex conjugate pair. So these are the poles of the system. There, pole pair. To make sure that this is the case, we can always plot them Z plane and Z P. This, if you give this a Z plane, this column vectors, it actually does not calculate anything. It just plots those zeros and poles on Z plane. If you give them the system coefficients, it actually calculates the zeros and poles. Okay, so we have about this picture, although mine is so much more artistic. How to calculate the corresponding system coefficients, A and B. So if the A was actually the system coefficients or polynomial coefficients of the system, and corresponding the zeros or poles are the roots of that polynomial. The inverse operation for roots is actually poly. Okay. So our let's see. Let's calculate first the A's. System coefficients are the polynomial coefficients defined by our poles. So these are the denominator coefficients. Coefficients are the polynomial defined by the poles. There. Ha! Wow. That's easy to calculate. Okay. Same thing for the numerator. This polynomial defined by the zeros. So this is the coefficients. And just reminder where these actually go. This is same as the b0 times x of n plus b1 times x of n minus 1, and so on this difference equation. Those are their corresponding coefficients. And again, quite easy to calculate that one too. At least for computer. There's a square root there, but anyways, it's of course square root of a constant. You can calculate once, and that's it. Okay, now we can play with this one. And the games we play, right, we need to first look at stem plot the first 10 values. Let's stem plot the first 10 values. If it's a FIR or IIR? Question mark. Yes, it's IIR because it has non-zero poles. I can see it already from here, but to make sure, let's take a look at the this impulse responses. That is certainly a test for if it's a impulse, the infinite impulse response or finite impulse response. So we take the impulse. For example, calculate first a vector of indexes, say 10. So this is basically just a region of interest for us. And then we can calculate the delta, which is simply casting double to if nn is equal to 0. I usually do it this way so that I have also a couple of values before the impulse starts. Okay, just for clarity, I don't like the pictures that have the data. First real data element is on the very first point there on the picture. All right, so that's the discrete delta function, so impulse. And now we can calculate the system output, which is simply, well, this is impulse response H equals filter B, A, and input. Okay, make sure that you have these on the right order. So always first you have the numerator polynomial coefficients, meaning the scaling factors of x, and then you have next one is the scaling factor of y, denominator coefficients, and then last one is the data. All right, and that's the system output for impulse. Input equals impulse response. There we go. And we can then plot it. Stem NN HH. Wow. Cool. I put impulse in and we got something that continues like that. Okay, there's a rule of thumb. You don't need to watch too far away on this data. It's just the highest order delay, which is in our case, the highest order delay is 2. If there's anything after that delay, meaning starting from delay 3 and further, if there's anything non-zero here, then it's IIR system. Okay, it has. So this is IIR system by definition. Non-zero output after highest order delay. Yeah. Good. IIR. And let's see what next. Frequency response for sampling rates, given sampling rate. Okay, let's take a look. Frequency response if sampling rate is okay, for fun I will mark it sampling rate for 2000 Hertz. It's just an example. So if this was a system with a 2000 Hertz sampling rate, so it's a data acquisition system, maybe some sort of, and that would be your perfect filter to filter out some noise. And now we can actually calculate the frequency response. Let's see. Yes, frequency response. And that can be calculated using Fretch. So let's take a look at help Fretch. There we go. So we have, wow, different ways of using it. BAN sampling rate. Yes, I want to use actually this form. So we have system coefficients B and A, and then actually the N means how many points you want on your plot. How many frequencies between 0 to Nyquist rate you want this to be calculated. And then you can actually put here the sampling rate. Then it actually scales the frequency response accordingly. So in this case, we're supposed to get a plot that looks something similar to this one. All right, so oops, Fretch. B, A, how many points? Well, it's up to it's your plot. One nice idea to have it on multiples of, well, or power of 2, just for fun, because actually it's then uses the fast Fourier transform to calculate this one. One way to calculate would be to do the 1024 point impulse response and calculate just the Fourier spectrum of that one. But, well, we have this Fretch function which does the same thing with a given sampling rate. And there we are. Wow, isn't that cool? Sort of. Let me make it a little bit bigger. All right. Not a bad filter at all. So how many calculations are we doing on this one? Fourth order. So it has 2 delays on both sides. So it has 3 or multiplying factors. We had 1 there, another -1. Okay, that's the same. Then we have 0.5 there, simple divide by 2. Then we have that's quarter of 1, 2 there. So in practice, there are only 1 floating point number needed to be calculated, the multiplication done. What else? We have 4 additions, 4 or 5 additions, that's something like that. A really fast, almost the same as 4-point running average filter. And we have some gain on the passband, about 18 dB, but on the other hand, this is minus 18 dB. So we have the stop band attenuation something like 35 dB compared to that 10 dB of running average. So with about the same amount of calculations, you can actually add, already about 20 dB to the stop band attenuation. Okay, and that's exactly why the IIR systems are used. You get a lot of stop band attenuation with very little damage to the signal. Okay, and it also says, okay, we had about, this is at 750 Hertz. Well, if this is 1000 Hertz, then 3/4 of that one is 750 Hertz, where the amplitude response goes to 0. And it looks more or less like that, quite say similar, except this is on linear scale. I'm not good at drawing, on logarithmic scale. This 0 gives me some trouble. Okay, so amplitude response is on top, and then the phase response is on the bottom, and we can clearly see this is not linear phase response system. Linear would mean exact line for the phase response. Okay. What else? So it's, yes, does the system have linear or non-linear phase response? Yes, this is very non-linear phase response in my case. Zeros and poles, okay, we did zeros and poles when we checked the that one. On the other hand, well, it doesn't hurt to call it again. So this was the zeros and poles based on the values we set, Z and P, and well, the same thing for B and A should look exactly the same, not similar, but exactly the same. Yes, it does. Of course it does. I calculated the coefficients based on those. All right. Then group delay. Okay, now I need to take a look at help. Group delay. Since I'm using Octal. GRP delay. I think this on MATLAB it's probably the same. Help. Help. GRP delay. Does it give? Check the MATLAB if it gives the help on that one. So, but group delay. Okay. Oops. Group delay. Usually the functions are quite similar. Number of samples and then sampling rate. So we call it quite similarly. So let's put it here. Frequency response. Not frequency response, but let's calculate the GRP delay. Wow. It actually also returns something. Okay. And this gives the time delay in samples. And it shows that, okay, at 250 Hertz, which is exactly the same angle where we have this pole, we have about 3 samples long, a little bit more than 3 samples long the time delay. But for example, the DC component only have about 1 sample delay. So it means that these different spectral components travel different time on that system. They come out on the different time with the time difference. Okay. That one? Oh, artifact. Okay. That one is artifact, but why? 750 Hertz. Can you calculate a phase shift when you don't have any signal? No, you cannot. So it's exactly that angle where you have 0 response. Yeah. So that why it gives this kind of artifact. You can actually so basically this one shows up on the frequency response. Let's take a look at that one. Frequency response. There. New figure. Okay. So we have the special point also on the frequency response where the amplitude response goes to 0, and then there's also the jump. It's actually a jump of pi on that one, so it means that the derivative goes haywire. Yeah. There. Okay, it depends on, okay, it probably calculates it on 1023 points. Or it does not, okay, maybe one calculates it from here to here, another calculates it from here to almost there. Yeah. Yeah, MATLAB probably includes also that point, since then it does not hit it exactly. Okay, let's see. Back to the theory or the exercise sheet. Scaling. Okay, this is fun. So how the scale, since the one, or basically the only problem with this filter is that it has not unity gain. So this also amplifies the signal. That's not good. How to calculate the maximum gain? Let's pull this one. Scaling. Oh, no. Scaling to unity gain. This is very simple thing. We first calculate the gain, which is maximum of absolute value of frequency response calculated of BBAA 1024. This is called brute force, by the way. FS, that doesn't need to be there, but just for fun. So exactly the same frequency response where you used to calculate the frequency response. If you use that one as an input argument, it actually returns the value. And then you can take the absolute value, which is the amplitude response part. The same way if you call angle of the frequency response is the phase response part. There. So this is the maximum amplitude response. Off. There. So it has that 8.363, which is about 18 dB. And next step, what we can do, we just multiply the whole thing with this one. Meaning practically you divide the numerator coefficients with this number. So BB equals BB divided by gain. This is the scaling to unity gain. And now we can calculate the frequency response again. Okay. Yeah, of course the artifact goes bigger, but anyway, let's see, zoom this one, something like that. Yeah, the maximum amplitude response here seems to be 0 dB, so it's a nice-ish filter. Not the perfect, since it has actually the DC is also a little bit affected. So it has, say, 3 dB, maybe 3 dB attenuation on the DC term. However, much better than running average already by amplitude response. So it would cut this random noise better than running average. Maybe. Okay, good. So that's basically the system analysis part of today. Next, let's generate some simple sound sample and try that. Well, you can actually do this one yourself. Okay, I will do something else instead. maybe. So using the filter. So let me make some data. Data x equals, I will just put there some constant value plus, no, should I put that one there? Well, why not? Not that big. Constant value plus some sinusoid there. Okay, 0.5 times sinusoid of 2 times pi, and something very slowly varying, maybe say just 50 hertz times sampling times. Okay, 0 with the 1 over fs to 0.5 seconds. All right, so this is about 1000 samples. And let me put some noise on it. X plus rand n size of xx, and amplitude for that one. Maybe the same amplitude as for the this sinusoid, and which would look like sorry, I didn't want to do that. Hopefully this will recover. Yes. Closes all the figures. All right, so xx is our xx 1000 points. Okay. Plot xxno. Something strange. Oh yes. Yes, of course. Thank you. It makes me a matrix. Thank you. Yeah. So that is my signal. Sort of, kind of. So it has some sinusoid signal at how many hertz? 50 hertz. So the 50 hertz sinusoid signal is somewhere in here. Somewhere in here. Definitely on the passband. And then it also has this the static value, and then it has some noise. And my claim is that now my system is probably filtering a bit of that noise. Not all of it. It's called noise reduction, no noise cancellation. Such as noise cancellation, it appears only when you turn the power off. Okay. So, using this system and calculating the output would be simple as using filter BB AA XNN XXNO. So this is the filtered signal. Let's put it on figure, new figure, and plot YY. And I just hope that I've reduced the noise. Yeah, seeing is believing. Right. So we have a low pass filter which does not affect on the constant value. It's still 1-ish around the same value. Not quite. Okay, there's a reason for that one. But then there's the now you can see that varying component, the sinusoid, much better. Not perfect. It still has some noise. Well, because I added some wide spectrum noise, and where I'm cutting only the basically upper half of it. When you take a look at the frequency response, oops, maybe I should actually do this one on different, better. Nice trick. We expand the filter a little bit. So the system actually has the 3 dB point around 260 hertz or so. Oh, actually, I don't know. This is more like 300 and something. About 330 hertz, 3 dB point. So basically, all the noise which is here hasn't been attenuated at all. Okay, so it cut only, say, higher spectral components. Good. Let's take a look at then a spectrogram, which is the last part. Okay. Sound samples. Hey, I have collected some sound samples. Just a moment. I will take one of those sound samples, download it, and or do I already have some of them here? Where it is? Where is the report? There. There I have one sound sample. I have a single sound sample. Yep, that kind of sound sample. Let me change the name to protect the innocent. Documents. There. All right. Now we are back. I uploaded or downloaded this kind of one of the returns with this sound sample here. Okay, shall I? Okay, so that's the sound sample. I can load the data. Let's see. That's strange. Help wave read. No, help audio read. There we go. Okay, so I have y fs equals audio read. File name is sample.wave. I hope this works. Yes, it does. So my sampling rate is 22050, and the sound actually sounds like this. Wow. Okay, did anyone recognize that one? Most of you probably. It's similar to whatever you did. So my question is, how does the spectrogram of that show anything? it's kind of boring sound. Single frequency. Let's make the spectrogram first. Okay. Yeah. Now there's a difference in MATLAB and this one. In MATLAB, there's a new function for the spectrogram, and Octave, there's still the old function. Let me also take this MATLAB spectrogram function. Select Sweden side. No. All right. They are a little bit different. So on MATLAB, it's called spectrogram, and you would use not this, but actually you would use almost the last. Yes. The form where you have this frequency location on vertical axis. Okay, on Octave it's called Specgram. So different name. On MATLAB it was used to be called Specgram. So just a different the name and some small things. Specgram. The parameters for spectrogram are data. Okay. Oops. Data, which is X. Well, that's my YY. Then we had number of points in our, how does it go? Yeah, the functions work similar. I just need to take a look at the easiest way of actually doing some of that spectrum to the power. Oh, okay. Window size. Good. They work the same. It's just the example is awkward. So first one is how many points you want to calculate on the this spectrogram. Okay, so it's Fourier transform. So it maps the data from 0 to sampling rate on n values. And most important part is the half of it. So if you have 1024 points, it means that actually this is mapped in 512 points, meaning that the delta F is sampling rate over the number of samples where you calculate this the Fourier transform. Okay, so why? I'll just put some numbers here. You will play with those later. So I will use 256 points, meaning that I have about 100 hertz the frequency resolution. Well, 22 kilohertz divided by 256 points is about 100, a little bit less than 100. Then the next point is the, let me take the help on spectrogram here. It's easier that way. Don't need to jump from one place to another. Oh, is it there? Okay, there. NFS, then window overlap, yes. Yeah, so spectrogram YY 256, sampling rate, then we have a number of points in window and number of points in overlap. I don't have any other reason than putting 256, same number on the window size as for the number of overlap, as long as this was the syntax. Just a moment. Window, yes. Overlap means, since this is calculating the spectrum for subsamples, how many points we move forward when we go and take the next subsample. So it's the overlapping value. How many points we want those subsamples to overlap. Unless you have any other number in mind, I use always the half way. So you don't move it those samples like this, but when you have one sample here, you take the next one there, then next, meaning that you will actually increase the time resolution. And next one is very important for MATLAB, especially the spectrogram should plot the frequency on y-axis. Otherwise, the default is it will put the frequency on this spectrogram on x-axis and time on y-axis. It's really awkward. This is what you get when you give a mathematician a job to do some subroutines for engineers. No offense, you know, mathematicians are fun people to work with, but okay. What did I do? Spectrum. What happens here? Invalid call. Yeah, because it doesn't have the y-axis here. Yeah, sorry, my fault. On MATLAB, you put the y-axis on at the end of the command on spectrogram. Okay, there we go. And that's the spectrogram of the beep from 0 to about 0.7 seconds. So that's 2 to the power of 14 points on that sample rate. It had about, well, 1.5 kilohertz tone. And this speckle here is the noise. So it's random noise, flat spectrum, meaning it's just a kind of gray value there, plus minus something. Yep. On chirp, you would expect to have it a straight line like that. Okay, so now we have analyzed the spectrogram, and now how about if I just want a certain time section here? Also a certain point here, I want one single spectrum on the middle of this data. Okay, let's see this. Probably the syntax is different on MATLAB. Okay. It has sampling rate goes to the last one. Yeah. So basically, I will draw the MATLAB corresponding command is. Wait a minute. All right. MATLAB spectrogram. Okay, FS is outplaced, and then it's number of points on FFT, then it's overlap, and then it's, let's see, I think it was that like that. See, yes, window overlap and FFT. Oh boy, yeah. 256 FS, and then y-axis. Yeah, good. So spectrogram, data, window size, overlap, how many points in fast Fourier transformation, sampling rate, then on primes you put that y-axis there, and it's single prime, not the double prime. Does it work now? Without y-axis it looks funny. It looks funny. Let it come and see how funny it looks like. Ah, yeah, you got some different data there, right? Yeah, makes sense. Yes, 2 kilohertz, and then you have one. Yeah. Yes, let's take a look at the what mine does look like on. Oops. So you probably got something like this, quite similar. So you have this low frequency part here. This is a constant value, so which is a 0 frequency. Then there's a 50 hertz signal and some noise. Boo. And playing with parameters. This looks ugly. You need more points on time, meaning that you can actually go and make overlap smaller. Or is it smaller or bigger? Overlap, I think it's smaller. No, it's bigger, sorry. Yeah. So remember, this is an image. This is really an image. Make it looking nice and descriptive. You can play with these parameters. What is the window size? What is the overlap? Even with the number of points on the FFT, you can play a little bit with that one to make it look nice. Okay, there we go. So that was the spectrogram. And now how to calculate a single spectrum of on the region of interest. So I will take a look at my XXNO and their values from 0.1000 to, well, 1000 plus 512, for example. There we go. So with the 512, wait a minute, not XXNO, Y. I don't have that many points on the XXNO. Y. Okay, that has lots of values at 16,000 samples. Okay, so Y equals, so first the region of interest, I will just mark it II equals from 1000 to 1000 plus 512. So this is my region of interest in indexes. And With this one, the corresponding frequency resolution would be length of that I. Wait a minute, not that way. Sampling rate divided by the length of the I. So this is the frequency resolution on the product. So about 42 hertz or 43 hertz frequency resolution if you use that many points of the data. If you need better frequency resolution, then you need to have more data. If you can deal with the less frequency resolution, then you have less data. Simple as that. Okay. And then my subsample would be YY sub equals to YY of II. So this is one way of selecting the data. You first have the regional indexes and then just select these indexed values. Okay. Next step would be to calculate the spectrum is to calculate the fast Fourier transformation. So YY sub F equals FFT of YY sub. Just simple Fourier transformation. And this is done by fast transforming it. The power spectrum of YY sub equals then YY sub F dot times complex conjugate of YY sub F. So this is the power spectrum. Ooh. But you know that if you calculate the power, you always use decibels, right? Okay. dB PYY sub. I will get in trouble with this naming conversion, but let's see. 10 times log 10 of PYY sub. Okay, that was already power, so it's 10 times in dB. Now we can actually start plotting, but actually let me next calculate also the frequency axis. The frequencies, corresponding frequencies. 0 to length of II minus 1. Okay, because I want the first value which comes out is the DC term, meaning the 0, and it has 1,000 and well, how as many values as you have on your FFT, you will actually divide this frequency axis on that many components, right? Minus 1 for fun, divided by length of II. So this gives me numbers from 0 to 1, basically, and if you multiply this by sampling rate, you will get the corresponding frequencies. There you go. And we can plot FF dB PYY sub. So that's the power spectrum. And with a twist. Oops. Oh no, yeah, I got into trouble. P, capital P. There we go. That's the full spectrum. Overlapping spectrum, actually. Actually, it's a repeating spectrum. So I don't need to plot it. I plotted it actually up here. So actually, what I need to do is just to half of it. That's also okay, but it has some extra data, and it is correct. Except that, okay, it shows the second half is basically the negative frequencies. Well, negative because these frequencies are the same as the negative frequencies. So let me change this a little bit. So need to plot only half of them. So let's plot from 1 to length of FF divided by 2. Okay. Oops. Same thing for that one. So from 1 to length. Length FF divided by 2. It's an old habit to put the parentheses, and then of course I usually miss a couple of those. Let's put one more. Yeah. Okay, so that's the spectrum in decibels, unreferenced decibels. So I didn't put any reference level for this one. On the other hand, well, it doesn't make any difference. Is usually when you have a data acquisition system, unless you calibrate it, you don't really know that value in any case. And if you want to calibrate the system, then you just, it's just a simple addition here, referencing. Okay, so this actually tells me I have a noise level around 18 dB, maybe somewhere here. White spectrum noise, white noise, spectrally very dull, and then it has this one peak at around 1500 Hertz or something like that. You can get better values by some graphic tools here. Do I have the tool as on Matlab? You can actually find the exact values here, but hey, wait a minute, it has shows the down here the coordinates on octave, so it's about 1479 hertz and about 45 decibels. And remember, this has plus minus 43 the hertz resolution. Okay, so those were the tricks to use on this exercise. Have fun with it. Hopefully you have more fun than on the first two exercises. And the deadline for this exercise was end of the week, right? Okay. One exception. Let's move this one week for further, since next week I'll be in Alcalá de Henares, which is next to Madrid. I'm having a teacher exchange trip there, and I will be there. I'm not here, so postpone the exercise unless I have already marked the time. Let's see. September. Okay, let me go and change that one immediately. So next week, I'm not here, so I'm not either reading the exercises there, probably. Usually I don't have any time, so that will be 23, that is right. 1 week further. I will also change the deadlines for the following exercises. Okay, good. Any questions? No? Done?